Hey everybody, we're back to talk about waves on a string. So this is going to review our waves equation and also bring in a new equation. This new equation isn't really on the AP test, but I'm bringing it up because sometimes it is given and then you're going to have to use it on the AP test. So let's get started talking about our two equations. So first, we have our regular old wave equation, which we talked about yesterday. We're also going to introduce, you should have seen this on the flipped lesson, but our equation for waves on a string. So this is only waves on a string. And this is just kind of like an extra equation that we have to help us understand a little bit more. So as a reminder here, F is always a force, and this is our force of tension. And this mu value is kind of similar to our mu for force of friction. It's just simply a proportion. So this is the mass over our length. Okay, and we're going to explore this. It's kind of a fun equation to practice rearranging equations and looking at relationships, which, as you all know, is my favorite thing to do. Our first problem, we are going to look at just a normal situation. And how do we know that? We say constant tension. So a wave on a string has constant tension. If the frequency is doubled, what is going to happen to the speed and the wavelength? So we have to use our regular old wave speed equation, okay? So we don't have to worry about our waves on a string equation, okay? So we're looking if we double F, okay? So I'm gonna first rearrange to solve for V. So V equals wavelength times frequency, okay? And if I double my frequency, V also doubles. That's my direct relationship. Next up, I want to look at wavelength. So I'm going to rearrange my equation once again. And if I double my frequency, okay, that's going to make my wavelength in half, okay, or by 1/2. Okay, let's move on to our next equation. Okay, let's move on to a problem where we are going to look at our second equation for waves on a string, which is my speed equals my tension over my mu. So this is asking if I would like to double the speed of a wave, what would I have to increase the tension? Okay, so let's think about this. If I wanted to double my velocity or speed, okay, we have to think about what would happen to my force. So 2 wouldn't make sense because that's the square root of 2. And if I did 4, that would give me, as we know, the square root of 4 is 2, okay? So if I need to double the speed, I need to increase my tension by a factor of 4. Cool. All right, so let's start to compare some different strings. So you might want to go back to waves on a string and kind of play around with this exact problem, okay? But we're just gonna kind of write it out, what's going on. So we have string number 1, which is a thicker string, and then we have string number 2, which is a thinner string. Okay, and we're gonna assume the length and the tension are the same. So our question is the speed of the waves on number 1 going to be greater, less than, or equal to the speeds on string 2? So let's head back to our equation for waves on a string. Okay, now as a reminder, this mu is mass over length, and we know for number 1 it is greater. Okay, now let's say that string number 1 is double the mass. So if I actually plug this in, we can tell pretty easily what's going to happen. So I have 2 mu, okay? And that means that my velocity would be the square root of 1/2 compared to our original one. So this means that my speed is less. And if I want an explanation, okay, number 2 would be the best one. A thick string implies a large mass per length and a slower wave speed. And we can tell that by our equation right here. All right, let's move on with some other problems that will conceptually and mathematically make us think a little bit more. Here are all the problems, so if you need to pause it and work on them, this is your chance to do it. Okay, let's look at these 2 strings in a different scenario. So let's say that still string 1 is thicker and they have the same length, except what's different now is they have equal speed, which means what about this tension has to be different? Okay, so let's focus on string 1. Okay, we know that it is a thicker string, so we know that mu is going to be larger. Okay, so if I need to make everything larger, that means that my tension force also has to be larger. Okay, why does that make sense? Well, V equals square root. Let's say I have double my mu. That means I also have to double my top. So that is now equal to the bottom string. What's my reasoning? My reasoning is number 1. String 1 must have a greater tension to compensate for its greater mass per length. Okay, kind of equal out my top and bottom. Okay, so let's head back to our regular old wave equation. So we have 3 waves and they propagate on strings with equal tensions and equal mass per length. So that means we can just use my regular old wave equation. Cool. So we're gonna order them of increasing. Okay, so we're gonna go from our small number to our big number. Okay, I'm saying this for a reason, just to remind myself. And if you did it backwards, no worries. So let's start with frequency. Okay, my smallest frequency is B, and then we have C, and then we have A. Cool. So let's go on to wavelength. Okay, now gotta look at this. My smallest wavelength is A. Okay, and then we have C, and then we have B. Okay, now this is kind of cool because we know that these are inverse relationships, and we can also tell that from our equation right here. Super cool connection that we have. Okay, so let's get started with our last part of this, where we are going to be talking about the speed. Okay. Now we know that these have equal tension, okay? And then they also have equal mass per length. So that means that all of my speeds are going to be exactly the same, okay? Just maybe a little bit different concept that we're thinking about here. And even though there's not numbers given for each of these, we can also look at this equation to help us out for that. So when we see waves that have equal tensions and equal mass per length, we can assume that all the speeds are exactly the same. However, our frequency and our wavelength may be a little different. Our last problem is pretty similar to something we've done before. So this one says a wave on a particular string travels with a speed of 16 meters per second. What factor should tension in the string be changed to get a speed of 32? So this point, it asks for tension, so we need to head back to this equation, okay? So I want to go from 16 to 32 meters per second, which means I am doubling, okay? So if I have 2V equals square root, I'm looking for something times F. Square root of what equals 2? Well, square root of 4 gives me 2. So I need 4 times the tension. Pretty cool. And here is a picture of my dog, Nacho. So don't forget that you need to upload a picture of your work and also submit that and click done. And then you will have an ungraded quiz after that. And then we're going to going to reevaluate what we want the rest of the class to look like.